Webb just revealed something massive, something astrophysicists secretly feared. Our fundamental understanding of the early universe might be wrong. For decades, the prevailing theory predicted a certain type of galaxy wouldn't exist this far back in time. Yet Webb's seeing them. Not just one or two anomalies, but a flood of fully formed massive galaxies where they shouldn't be. The data reveals a universe far more mature, far more quickly assembled than anyone predicted. What does this mean for the Big Bang theory? Let's examine. 600 galaxies, all breaking the rules. The James Webb Space Telescope wasn't supposed to find so many massive, fully formed galaxies so early in the universe's history. These galaxies are so large, so bright, and so old that they simply shouldn't exist according to our current understanding of cosmology. It's like finding fully grown oak trees, sprouting mere weeks after the first seeds were sown. Consider the timeline. The Big Bang occurred roughly 13.8 billion years ago. For the first few 100 million years, the universe was a chaotic soup of plasma. Gravity began to coalesce matter, forming the first stars and eventually the first galaxies. Our models predicted that these early galaxies would be small, irregular, and slowly accreting mass over billions of years. Webb's data reveals something else entirely. These impossible early galaxies, as some scientists are calling them, are behemoths. They're not the faint fledgling galaxies we expected. They're mature, spiral galaxies brimming with stars, some reaching sizes comparable to our own Milky Way. One of the most perplexing aspects is their mass. Some of these galaxies are estimated to contain hundreds of billions, even trillions of stars. Assembling such a vast amount of mass in such a short time frame defies our current models of galaxy formation. The universe, according to these new observations, was far more efficient at building galaxies than we ever imagined. The implications extend beyond just galaxy formation. These early behemoths also challenge our understanding of dark matter, the mysterious substance that makes up about 85% of the universe's mass. Dark matter is believed to play a crucial role in the formation of galaxies, providing the gravitational scaffolding that allows ordinary matter to coalesce. The problem? If these massive galaxies formed so quickly, it suggests that dark matter was even more influential in the early universe than previously thought. Either dark matter interacted with ordinary matter in ways we don't yet understand, or there's something fundamentally wrong with our understanding of dark matter itself. Here's what's wild. These galaxies are not some statistical fluke. They're not a few isolated anomalies that can be easily dismissed. Webb is finding them everywhere it looks. The deeper it peers into the early universe, the more of these impossible galaxies it uncovers. Scientists discovered that the light from these distant galaxies is stretched or redshifted due to the expansion of the universe. The higher the redshift, the farther away the galaxy and the earlier in the universe's history it existed. Webb is detecting galaxies with redshifts of 8, 9, and even 10 or higher. This corresponds to a time when the universe was only a few 100 million years old. The analysis continued. Further examination revealed that these galaxies are not only massive but also surprisingly metal-rich. In astronomy, metals refer to any element heavier than hydrogen and helium. These elements are forged in the cores of stars and then dispersed into the universe through supernova explosions. The presence of heavy elements in these early galaxies suggests that star formation was incredibly rapid and efficient. It means that massive stars were born, lived, and died in a cosmic blink of an eye, enriching the surrounding gas with metals. This rapid cycle of star formation is another puzzle that challenges our current models. This means that the early universe was not the pristine, metal-poor environment we once thought it was. It was a dynamic and chaotic place, teeming with activity and capable of building massive galaxies far faster than we predicted. The implications extend to the very fabric of our cosmological models. If our understanding of galaxy formation is wrong, what else are we missing? Could there be fundamental flaws in our understanding of dark matter, dark energy, or even the Big Bang itself? Measurements showed the size and luminosity of these galaxies simply shouldn't be possible, given the age of the universe at that time. It's like finding a fully furnished mansion in a newly discovered country that's only been populated for a few decades. Where did all the materials come from? How was it built so quickly? Scientists are scrambling to revise their models, incorporating these new observations from Webb. Some are proposing alternative theories of galaxy formation, while others are exploring new ways in which dark matter might have influenced the early universe. This discovery is not just a minor adjustment to our existing theories, it's a major paradigm shift that could rewrite our understanding of the cosmos. It's a reminder that the universe is full of surprises and that our current knowledge is just a tiny piece of a much larger puzzle. And then, the even deeper images started coming in. Ever wonder if the universe is expanding at the rate we think it is? Because that's precisely what's being called into question. It's not just a minor discrepancy, it's a full-blown crisis in cosmology known as the Hubble tension, and the James Webb Telescope is amplifying it. The Hubble constant, for those unfamiliar, is the rate at which the universe is expanding. We have two primary ways of measuring it. The first involves observing distant supernovae, such as exploding stars, and using them as standard candles to gauge cosmic distances and expansion rates. This method, primarily employed by the Hubble Space Telescope, gives us one value for the Hubble constant. The second method relies on studying the cosmic microwave background, CMB, the afterglow of the Big Bang. By analyzing the patterns in the CMB, we can infer the Hubble constant based on our understanding of the early universe and how it has evolved. This method gives us a different value. These two values should agree. They don't, and the gap between them is what we call the Hubble tension. Before Webb, there was hope that the tension might be due to some systematic errors in our measurements of supernovae distances. Perhaps there was some subtle effect we weren't accounting for, some dust obscuring our view, or some quirk in the supernova themselves. Webb was supposed to help resolve this. With its superior infrared vision, Webb can peer through dust clouds and make more precise measurements of these distant supernovae. The expectation was that Webb would refine the supernova distance measurements and bring them into closer alignment with the CMB-derived value. Instead, Webb has largely confirmed the Hubble measurements. The supernova distances appear to be accurate. The problem isn't with the supernovae, the problem goes deeper. This is where the fear comes in. If the supernova measurements are correct and the CMB measurements are correct, then our entire cosmological model, the framework we use to understand the universe, may be incomplete or even wrong. It would mean there's something fundamental we're missing about the nature of dark energy, dark matter, or even gravity itself. Think about it. We're talking about the foundations of our understanding of the cosmos. The Hubble tension isn't just a small disagreement over a decimal point. It's a potential crack in the very foundation upon which our cosmological theories are built. So, what could be causing this tension? One possibility is that our understanding of dark energy is incomplete. Dark energy is the mysterious force that's driving the accelerated expansion of the universe. If dark energy behaved differently in the early universe than it does today, it could explain the discrepancy between the CMB-derived Hubble constant and the supernova-derived Hubble constant. Another possibility is that there's some new type of particle or interaction that we haven't yet discovered. This new physics could have affected the expansion rate of the early universe and left its imprint on the CMB. A third possibility, and perhaps the most radical, is that our understanding of gravity itself is flawed. Einstein's theory of general relativity has been incredibly successful in explaining the behavior of gravity on large scales, but it may break down at the very largest scales or at the very beginning of the universe. Scientists are exploring all of these possibilities and many more. The Hubble tension has become one of the most pressing problems in cosmology, and it's driving a flurry of theoretical and observational research. The implications extend to our understanding of the age of the universe. If the Hubble constant is higher than we thought, then the universe is younger than we thought. This could create further problems, as it would mean that some of the oldest stars in the universe are older than the universe itself. This is where those early galaxies discovered by Webb come back into play. If the universe is younger, then those galaxies had even less time to form, and making their existence even more puzzling. It all ties together. The Webb data isn't just confirming that the Hubble tension is real, it's also highlighting the interconnectedness of all these cosmological puzzles. The early galaxies, the Hubble constant, dark energy, dark matter, they're all pieces of the same puzzle, and we need to solve them all together if we want to understand the universe. Scientists are now re-examining the assumptions that underpin our cosmological models. Are we making any hidden assumptions that could be leading us astray? Are there any alternative theories that could explain the Hubble tension and the existence of these early galaxies? Measurements showed these early galaxies shouldn't exist, and now these same measurements are suggesting that the universe itself isn't behaving as we thought it would. It's a challenge to everything we thought we knew. The analysis continued. This kept me up last night. Forget the early galaxies for a second, and let's talk about dark matter. We've always assumed it's distributed in a certain way, a kind of scaffolding upon which galaxies form. What if that assumption is wrong? What if dark matter isn't where we thought it was? Remember, dark matter doesn't interact with light. We can't see it directly. We infer its presence by its gravitational effects on visible matter. Galaxies rotate faster than they should based on the visible matter, alone implying the existence of extra, unseen mass. We map this dark matter by observing how it bends light from distant galaxies, a phenomenon called gravitational lensing. The standard model of cosmology predicts that dark matter should be more concentrated in the centers of galaxies and galaxy clusters, forming dense halos that pull in ordinary matter and drive galaxy formation. Simulations based on this model have been remarkably successful in reproducing the large-scale structure of the universe. However, Webb's observations are starting to challenge this picture. Consider the early galaxies that Webb has been observing. If they formed in a universe dominated by dark matter halos, they should be surrounded by these halos. These halos should, in turn, affect the distribution of ordinary matter within the galaxies, influencing their shape and rotation. But what if these early galaxies don't have the expected dark matter halos? What if the dark matter is more spread out, less concentrated, or even missing? That's the implication some scientists are starting to draw from the Webb data. Here's what's wild. If dark matter is less concentrated in the early universe than we thought, it would have profound implications for our understanding of galaxy formation. It would mean that galaxies form through different mechanisms than we currently believe. It might even suggest that our understanding of dark matter itself is incomplete. Scientists discovered that the light from these early galaxies wasn't being lensed in the way they expected. The gravitational lensing signal was weaker than predicted, suggesting that the dark matter halos around these galaxies were less massive or less concentrated than anticipated. In some cases, there was almost no lensing signal at all. This raises some fundamental questions. Where is the dark matter? Did it ever exist in the expected concentrations? Or is our understanding of gravity itself flawed, leading us to misinterpret the evidence? The implications extend to our understanding of the cosmic web, the large-scale network of filaments and voids that permeates the universe. Dark matter is thought to be the backbone of the cosmic web, with galaxies forming along its filaments. If the distribution of dark matter is different than we thought, then the structure of the cosmic web could also be different. Measurements showed that this discrepancy could also explain the Hubble tension. If dark matter is less concentrated, it would have a different effect on the expansion rate of the universe, potentially reconciling the different measurements of the Hubble constant. This is a big deal. It's not just a minor tweak to our models. It's a potential paradigm shift that could rewrite our understanding of the universe. Further examination revealed that some early galaxies appear to be surprisingly small and compact, even smaller than predicted by simulations. This could be another sign that dark matter isn't playing the role we thought it was. If galaxies formed within massive dark matter halos, they should be larger and more diffuse. The fact that they are so small and compact suggests that they form through different processes. Scientists are now exploring alternative theories of dark matter that could explain these observations. One possibility is that dark matter is made up of lighter particles than we currently assume. These lighter particles would move faster and be less likely to clump together, resulting in a more diffuse distribution of dark matter. Another possibility is that dark matter interacts with itself or with ordinary matter through forces other than gravity. These interactions could affect the distribution of dark matter and prevent it from forming dense halos. Of course, it's also possible that our understanding of gravity is incomplete. Modified Newtonian dynamics, RMOND, is an alternative theory of gravity that attempts to explain the observed rotation curves of galaxies without invoking dark matter. While MONDA has been largely dismissed by the scientific community, it's experiencing a resurgence of interest in light of the Webb data. The analysis continued, with scientists meticulously comparing the Webb observations with the predictions of different cosmological models. They're looking for any discrepancies that could provide clues about the nature of dark matter and the formation of galaxies. This means every single galaxy formation simulation ever done may need to be revisited. Think about the computational power, the years of work, all predicated on a distribution of dark matter that might simply be wrong. It's a sobering thought. And then there's the even more unsettling possibility. Maybe dark matter isn't what we think it is at all. Maybe it's not even there, and we need a completely different framework to understand the universe. The Webb data is forcing us to confront these uncomfortable questions. It's challenging our most basic assumptions about the universe and pushing us to think outside the box. The implications are enormous. If our understanding of dark matter is flawed, it could affect everything from our understanding of the formation of galaxies to our understanding of the fate of the universe. It could even lead to new discoveries in particle physics and fundamental physics. This is not just an astronomy story, it is a story about science itself. It's about the power of observation to challenge our preconceived notions and push us to explore new frontiers. It's a reminder that even our most successful theories are always subject to revision in the light of new evidence. The Webb telescope is not just showing us pretty pictures of galaxies. It's showing us the universe in a new light, revealing its secrets and challenging us to rethink everything we thought we knew. Scientists are now scrambling to develop new models that can explain the Webb observations. They're running new simulations, exploring alternative theories and designing new experiments to test their ideas. It's a time of great excitement and uncertainty in the field of cosmology. Here we have measurements showing that the distribution of dark matter isn't what we thought, and these same measurements are suggesting that the universe itself may not be behaving as we thought it would. That's two reality checks in one. Meanwhile, all this uncertainty forces us to reevaluate some of our most cherished assumptions. The next step is to examine how this all affects dark energy. December 2022. A team at Penn State was running simulations of early galaxy formation. They expected to see gas collapsing inwards, forming stars at the center, and then gradually the galaxy building outwards. Pretty standard stuff. What they actually saw, something almost backwards. Stars forming not in the calm center, but in turbulent outskirts. Galaxies appearing almost inside out. It wasn't a subtle difference. It was like watching a movie of galaxy formation played in reverse. Consider how galaxies are supposed to form. Dark matter provides the gravitational scaffolding, gas falls in, that gas compresses, and then ignites into stars. These stars, born in the dense center, then influence the surrounding gas, leading to further star formation. But Webb's data, combined with these simulations, is painting a different picture. A picture where star formation is happening in the least expected places. Far out in the galactic disk, in regions thought to be too diffuse, too turbulent, too unstable to actually birth stars. How can stars even form in these conditions? That's the question that has cosmologists scratching their heads. The old model relied on a nice, neat progression. Gravity wins, gas collapses, stars ignite. This new data is suggesting something far messier. Maybe external factors like smaller galaxies merging or intergalactic gas streams are playing a much bigger role than previously thought, triggering star formation from the outside in. Let's examine this a bit. Imagine throwing a pebble into a still pond. The ripples spread out, right? That's how we used to think of star formation, a central event creating outward effects. But what if instead you had dozens of pebbles thrown in from all sides, creating a chaotic mess of overlapping ripples? That's closer to the picture Webb is giving us. Now, it's crucial to remember that we're not talking about subtle variations here. We're talking about fundamental disagreements between theory and observation. The simulations, even when tweaked to account for various factors, still struggle to reproduce the extent of this outside-in star formation. They can't quite get the number of stars forming in these unexpected regions. And they definitely can't explain why so many early galaxies seem to exhibit this behavior. This isn't just about tweaking parameters in a computer model. This is about questioning the underlying assumptions of galaxy formation itself. Are we underestimating the role of environmental factors? Are we missing some key physics that governs the behavior of gas in these extreme environments? And it gets even weirder. The types of stars forming in these outer regions seem to be different too. They tend to be more massive, hotter, and shorter-lived than the stars found in the galactic centers. This suggests that the conditions for star formation are not only different, but also lead to a different kind of stellar population. Measurements showed that these massive stars, in turn, can have a huge impact on their surroundings. Their intense radiation and powerful stellar winds can actually disrupt the gas clouds around them, preventing further star formation. It's a self-regulating process, but one that we don't fully understand. The implications extend beyond just galaxy formation. These massive, short-lived stars are also responsible for seeding the universe with heavy elements, the building blocks of planets and life. If they're forming in unexpected places, that could change our understanding of how these elements are distributed throughout the cosmos. Here's what's wild. If star formation isn't happening the way we thought it was, then the whole timeline of galaxy evolution could be off. We might be misinterpreting the ages of galaxies, the rates at which they're forming stars, and even the processes that drive their growth. It's like trying to assemble a puzzle with the wrong picture on the box. You might get some pieces to fit, but the overall image will be distorted. Consider this. Our understanding of the chemical evolution of galaxies is heavily based on models of star formation. We assume that stars are born with a certain mix of elements and that they then enrich their surroundings as they age and die. But if the stars themselves are different, and if they're forming in different environments, then those models need to be completely rewritten. The analysis continued. Another group at Cambridge focused on the spiral galaxy M74. What they found there was even more perplexing. Not only were the outermost arms birthing stars at an accelerated rate, but those stars were showing spectral lines that defied all explanation. It was as if they were made of elements that shouldn't even exist in those quantities. Scientists discovered that something strange was happening with the way light was being absorbed and emitted in these regions. The standard models of stellar atmospheres simply couldn't account for the observations. They were seeing things that, according to our current understanding of physics, shouldn't be possible. And then there's the issue of galactic magnetic fields. These fields are thought to play a crucial role in regulating star formation by providing pressure support against gravity. But the Webb data is suggesting that these fields are much weaker and more disorganized than previously thought, particularly in the outer regions of galaxies. This raises the question, how can stars form at all if there's not enough magnetic pressure to stabilize the gas clouds? This means that our picture of galaxy formation is not just incomplete, it might be fundamentally flawed. We need to go back to the drawing board and rethink our basic assumptions about how galaxies evolve. What does this mean for dark energy? We thought metallicity was straightforward. Higher metallicity, more star formation. Lower metallicity, less. But the James Webb data is painting a far more complex and, frankly, baffling picture. Metallicity, for those unfamiliar, is astronomers' shorthand for the abundance of elements heavier than hydrogen and helium in a star or gas cloud. These heavier elements are forged in the cores of stars and then scattered throughout the galaxy when those stars die. So a higher metallicity generally indicates a more chemically evolved environment, one that's been seeded with the products of previous generations of stars. The expectation was that regions with higher metallicity would be more efficient at forming stars. More heavy elements mean more efficient cooling of gas clouds, allowing them to collapse more readily under gravity. More efficient collapse, more stars. It seemed logical. But Webb's observations are turning this neat picture on its head. The telescope is showing us regions of galaxies, particularly in the outer arms of spirals where star formation is rampant despite relatively low metallicities. In some cases, these regions have metallicities comparable to those found in the very early universe, when galaxies were just beginning to form. Yet, they're churning out stars at rates that rival or even exceed those seen in the metal-rich inner regions of galaxies. How is this possible? One possibility is that we're simply misunderstanding the relationship between metallicity and star formation. Perhaps there are other factors at play that are more important than metallicity in certain environments. Things like the density of the gas, the strength of magnetic fields, or the presence of feedback from previous generations of stars. Maybe these factors can compensate for the lack of heavy elements, allowing star formation to proceed even in metal-poor environments. Another possibility is that the metallicity measurements themselves are wrong. It's notoriously difficult to accurately determine the metallicity of a star or gas cloud, especially at large distances. Astronomers rely on analyzing the light emitted by these objects, looking for specific spectral lines that correspond to different elements. But these spectral lines can be affected by a variety of factors, such as temperature, density, and the presence of dust. It's conceivable that we're underestimating the true metallicity in these regions due to some systematic error in our measurement techniques. And then there's the question of where these elements are. Are they evenly distributed throughout the gas clouds, or are they concentrated in small, dense pockets? If the heavy elements are clumped together rather than uniformly mixed, then they might be more effective at promoting cooling and star formation, even if the overall metallicity is low. This metallicity distribution function is something astronomers are only beginning to explore in detail, thanks to Webb's unprecedented resolution. The implications of this metallicity mystery are far-reaching. If our understanding of the relationship between metallicity and star formation is flawed, then it throws into question much of what we think we know about galaxy evolution. Our models of how galaxies form and grow are heavily based on the assumption that metallicity plays a key role in regulating star formation. If that assumption is wrong, then those models need to be revised. Consider the early universe. Astronomers believe that the first galaxies were extremely metal-poor, since they formed before there were many stars to produce heavy elements. Yet these early galaxies were also incredibly prolific star-forming regions. If low metallicity is supposed to suppress star formation, then how did these galaxies manage to form so many stars? The Webb data is forcing us to confront this paradox head-on. We need to develop new theories and models that can explain how galaxies can form stars efficiently, even in the absence of heavy elements. This will require a deeper understanding of the physical processes that govern star formation, as well as more sophisticated techniques for measuring metallicity in distant galaxies. It's not just about understanding the past either. The metallicity mystery also has implications for the future of our own galaxy, the Milky Way. The outer regions of the Milky Way are relatively metal-poor compared to the inner regions. If star formation can proceed efficiently in these metal-poor environments, then it suggests that the Milky Way may continue to grow and evolve for billions of years to come, even as its supply of heavy elements is gradually depleted. The metallicity mystery highlights the importance of observational data in challenging and refining our theories. For decades, astronomers have relied on theoretical models and computer simulations to understand galaxy evolution. But these models are only as good as the assumptions that go into them. The Webb data is providing us with a crucial reality check, forcing us to reevaluate our assumptions and develop more accurate models. Here's what's wild. The more we learn, the more we realize how much we don't know. And that's what makes science so exciting. What about dark matter? There's a fundamental problem with our understanding of the first billion years of the universe. We see these incredibly bright, massive galaxies forming way back then, churning out stars at rates that, according to our models, should be impossible. The issue boils down to this. Our current models of galaxy formation heavily rely on the presence of heavy elements, what astronomers call metals, to cool down the gas clouds that collapse to form stars. These elements, like carbon, oxygen, and iron, radiate away heat, allowing the gas to become denser and more prone to gravitational collapse. But the early universe was a very different place. It was largely devoid of these heavy elements. The first stars, population 3 stars, forged these elements in their cores and then scattered them across the cosmos in supernova explosions. But that process takes time. So, the galaxies forming in the first billion years existed in a relatively metal-poor environment. According to our models, this lack of metals should have severely hampered star formation. Without efficient cooling, the gas clouds would have remained too hot and diffuse to collapse into stars. Yet the Webb telescope is showing us that these early galaxies were anything but quiescent. They were star-forming powerhouses, churning out stars at rates that dwarf anything we see in the local universe today. So, what's going on? How did these galaxies manage to form so many stars, despite the lack of heavy elements? One possibility is that our understanding of how metals affect star formation is incomplete. Perhaps there are other mechanisms, besides radiative cooling, that can trigger the collapse of gas clouds in metal-poor environments. For example, turbulence or magnetic fields could play a more significant role than we previously thought. Another possibility is that the early universe was simply different. Perhaps the conditions in the first billion years were so extreme that they overrode the usual constraints on star formation. For example, the density of the intergalactic medium might have been much higher back then, making it easier for gas clouds to collapse, even in the absence of metals. Or perhaps we're underestimating the amount of metals that were actually present in these early galaxies. It's notoriously difficult to measure the metallicity of distant galaxies, and our current techniques may be missing some crucial information. The Webb telescope, with its unprecedented sensitivity and resolution, is helping us to refine these measurements, but there's still a lot of uncertainty. The Webb data reveals a new population of faint, extremely distant galaxies that are far more metal-poor than we previously thought possible. These galaxies are providing us with a unique window into the conditions that prevailed in the early universe, and they're challenging us to rethink our assumptions about galaxy formation. This isn't just an academic exercise. Understanding how galaxies formed in the early universe is crucial for understanding how the universe evolved to its present state. The first galaxies were the seeds of all the galaxies we see around us today, including our own Milky Way. If we don't understand how these seeds were planted, we can't fully understand the growth of cosmic structure. The implications extend beyond galaxy formation. The heavy elements produced by the first stars played a crucial role in the formation of planets and the emergence of life. If we don't understand how these elements were produced and distributed in the early universe, we can't fully understand the origins of life itself. Scientists discovered that the early universe may have had different physical laws. It's a radical idea, but it's one that's gaining traction in the face of the Webb data. Perhaps the fundamental constants of nature, like the gravitational constant or the fine structure constant, were slightly different in the early universe, affecting the way that galaxies formed and stars evolved. Of course, this is all highly speculative. We're still in the early stages of analyzing the Webb data, and it will take years of research to fully understand its implications. But one thing is clear: the Webb telescope is revolutionizing our understanding of the early universe, and it's forcing us to confront some of the biggest mysteries in cosmology. Here's what's wild. The very act of observing these distant galaxies is changing them. The light that we're detecting from them has traveled for billions of years, and in that time it has been stretched and redshifted by the expansion of the universe. This means that the light we're seeing is not exactly the same as the light that was originally emitted. The expansion of space itself alters the light. It's like trying to understand a painting by looking at a distorted reflection of it. The analysis continued. Scientists are developing new techniques to correct for these effects, but it's a challenging task, and it highlights the fundamental limitations of our ability to study the early universe. We can never truly see it as it was. We can only see a distorted image of it, filtered through the lens of cosmic expansion. This means that we have to be very careful about interpreting the Webb data. We can't simply take the images at face value. We have to account for all the various effects that could have distorted the light along its journey to Earth. Despite these challenges, the Webb telescope is providing us with an unprecedented glimpse into the early universe, and it's giving us a new appreciation for the complexity and beauty of the cosmos. The first billion years may always remain somewhat mysterious, but thanks to Webb, we're finally starting to piece together the puzzle. And then there's the question of supermassive black holes. Webb actually revealed something massive. The simulations? They're struggling to keep up. For years, cosmologists have built incredibly complex computer models to simulate the formation and evolution of galaxies. These simulations, often run on the world's most powerful supercomputers, are designed to mimic the processes that shaped the universe after the Big Bang. They incorporate everything we think we know about gravity, dark matter, gas dynamics, and star formation. The idea is that if we start with the initial conditions of the early universe, we should be able to recreate the kinds of galaxies we see today. But the Webb telescope is throwing a wrench into the works. The galaxies Webb is observing in the early universe are far more massive and mature than the simulations predicted. They have well-defined spiral arms, central bulges, and supermassive black holes at their centers. All features that, according to our models, shouldn't have had time to form in the first billion years after the Big Bang. It's as if we gave the simulations the wrong recipe. We thought we understood the ingredients: gravity, dark matter, gas, but the final product is completely different from what we expected. This suggests that there's something fundamentally wrong with our understanding of galaxy formation. Consider the problem of supermassive black holes. These behemoths, millions or even billions of times the mass of the Sun, lurk at the centers of most large galaxies. How did they get so big so quickly? According to our current models, black holes grow by gradually accreting matter from their surroundings. But this process is relatively slow. It shouldn't have been possible for supermassive black holes to reach their observed sizes in the early universe. Webb's observations suggest that these black holes may have formed through a different mechanism, one that allows them to grow much more rapidly. Perhaps they formed directly from the collapse of massive gas clouds, or perhaps they merged with other black holes to quickly build up their mass. We just don't know. The problem extends beyond black holes. The simulations also struggle to reproduce the observed abundance of massive galaxies in the early universe. There are simply too many of them. This suggests that galaxies formed more efficiently in the early universe than our models predict. Maybe the rate of star formation was higher, or maybe galaxies merged more frequently. Again, we're missing something crucial. Scientists are now scrambling to revise their simulations to better match the Webb data. They're tweaking parameters, adding new physics, and exploring alternative scenarios. But it's a challenging task. The models are already incredibly complex, and it's not always clear which changes will produce the desired results. One promising avenue of research involves exploring the role of dark matter. Dark matter is an invisible substance that makes up about 85% of the matter in the universe. It interacts with ordinary matter through gravity, and it plays a crucial role in the formation of galaxies. Our current models assume that dark matter is cold, meaning that its particles move relatively slowly. But some scientists have proposed that dark matter may be warm, meaning that its particles move faster. Warm, dark matter would suppress the formation of small-scale structures in the early universe, which could lead to the formation of more massive galaxies. Another possibility is that our understanding of gravity is incomplete. Einstein's theory of general relativity has been incredibly successful at explaining the behavior of gravity on large scales, but it may break down in the extreme conditions of the early universe. Some scientists are exploring alternative theories of gravity that could lead to different rates of galaxy formation. The truth is, we're still in the dark about many aspects of galaxy formation. The Webb telescope is shining a light on these unknowns, and it's forcing us to rethink our fundamental assumptions about the universe. It's a humbling experience, but it's also an exciting one. What this means is that some of the most fundamental assumptions that were baked into those original computer models are now being questioned. The speed at which galaxies could form, the mechanics of black hole creation, the very nature of dark matter, all of these are back on the table. This isn't just about tweaking a few numbers in a computer program. This is about potentially rewriting the textbooks on cosmology. And that's a task that will take years, if not decades, of dedicated research. It's a field-wide recalibration. But it highlights how crucial observation is in science. Theories are great, simulations are powerful. But ultimately, it's the data that decides what's real and what isn't. And right now, the data is telling us that our simulations have some serious catching up to do. The early universe, it seems, was far more dynamic and surprising than we ever imagined. The implications extend far beyond just galaxy formation. It touches on our understanding of the fundamental laws of physics. And then there's the question of the limits of observation itself. The implications extend beyond just tweaking our models. It raises a really profound question. Is our current understanding of physics complete? Consider the sheer scale of the discrepancy we're seeing. These early galaxies are far too massive, far too quickly formed, and far too numerous for what our current theories predict. It's not a minor deviation, it's a major gap. And when you encounter a gap this large, you have to start asking whether the underlying framework itself needs to be re-evaluated. Are we missing something fundamental about how the universe works? Now, the standard model of particle physics has been incredibly successful. It explains a huge range of phenomena with remarkable accuracy. But it's not perfect. We know there are things it doesn't explain, like dark matter, dark energy, and the origin of neutrino masses. Could it be that these unexpected galaxy formations are somehow linked to these gaps in our understanding? Could it be that the early universe was governed by physical laws that are slightly different from what we observe today? It's a radical idea, of course, but science progresses by challenging existing paradigms, and the Webb telescope is giving us data that is forcing us to confront some very uncomfortable questions. Let's examine a few possibilities. One is that there are undiscovered particles or forces that played a significant role in the early universe. These particles could have interacted with dark matter or ordinary matter in ways that accelerated galaxy formation. Another possibility is that our understanding of gravity is incomplete, even beyond the modifications that try to explain dark matter. Einstein's theory is incredibly successful, yes, but we already know it breaks down at the singularity of a black hole. Could there be other regimes, like the extreme densities of the early universe, where general relativity needs to be modified? Some physicists are exploring theories of modified Newtonian dynamics, or MOND, which propose that gravity behaves differently at very low accelerations. Others are looking at theories involving extra dimensions or alternative formulations of quantum gravity. These are all highly speculative ideas, but they are not without merit. They are motivated by the need to explain the observed discrepancies in the universe, and they offer potentially testable predictions. The data reveals something else too. Perhaps it isn't new physics, but rather new applications of existing physics that we haven't considered before. Could it be that we're underestimating the role of magnetic fields in galaxy formation, or the impact of high-energy cosmic rays, or the effects of quantum entanglement on cosmological scales? It's also crucial to remember that our simulations are based on certain assumptions about the initial conditions of the universe. We assume that the universe was homogeneous and isotropic on large scales, meaning that it was uniform in all directions. But what if this assumption is not entirely correct? What if there were subtle variations in the density or temperature of the early universe that had a significant impact on galaxy formation? These variations could have been seeded by quantum fluctuations during inflation, the period of rapid expansion that is believed to have occurred shortly after the Big Bang. If these fluctuations were larger or more complex than we currently assume, they could have led to the formation of more massive galaxies at earlier times. The point is, there are many possibilities to consider, and the Webb telescope is providing us with the data we need to test these ideas. It's a process of trial and error, of building models and comparing them to observations, of refining our understanding of the universe one step at a time. This isn't just about theoretical physics either. It has implications for our understanding of the fundamental constants of nature. We assume that these constants, like the speed of light and the gravitational constant, are the same throughout the universe and throughout time. But what if they varied slightly in the early universe? Some physicists have proposed that the fundamental constants may have been different at earlier times, and that this could have affected the rate of galaxy formation. This is a highly controversial idea, but it is not without evidence. There are some observations of distant quasars that suggest that the fine structure constant, which determines the strength of electromagnetic interactions, may have been slightly different in the early universe. If this is true, it would have profound implications for our understanding of physics. It would mean that the laws of nature are not as immutable as we thought they were, and that they can evolve over time. It would also open up the possibility of new physics beyond the standard model. Of course, it's also possible that the problem lies not with our understanding of physics, but with our understanding of astrophysics. Galaxy formation is a complex process that involves many different factors, including gravity, gas dynamics, star formation, and black hole feedback. It could be that we are simply missing some key ingredients in our models. For example, we may be underestimating the role of mergers in galaxy formation. When two galaxies collide, they can merge together to form a larger galaxy. This process can trigger bursts of star formation and accelerate the growth of supermassive black holes. It could be that mergers were more common in the early universe than we currently assume, and that this led to the formation of more massive galaxies. Or it could be that we're underestimating the amount of gas that was available for star formation in the early universe. Gas is the raw material for stars, and the more gas a galaxy has, the more stars it can form. It could be that the early universe was richer in gas than we currently assume, and that this allowed galaxies to form more quickly. The analysis continued. Scientists discovered something else. It's possible that the supermassive black holes at the centers of these early galaxies played a more significant role in their formation than we previously thought. These black holes can release vast amounts of energy in the form of jets and outflows, which can heat up the surrounding gas and suppress star formation. It could be that these black holes were more active in the early universe, and that this helped to regulate the growth of galaxies. Whatever the explanation, it's clear that the Webb telescope is forcing us to rethink our assumptions about the early universe. It's a humbling experience, but it's also an incredibly exciting one. We're on the verge of a new era of discovery, and we're poised to learn more about the universe than ever before. And then there's the issue of small sample sizes. You've been sold a simplified story about the cosmos. The neat, tidy timeline from the Big Bang to galaxies like our Milky Way. The James Webb Space Telescope is throwing a wrench into that narrative, and one of the most profound implications is the resurgence of interest in alternative cosmological models. Now, before anyone gets too excited, we're not talking about fringe theories plucked from the internet. We're talking about scientifically grounded models that, for various reasons, haven't gained mainstream traction until now. The standard model of cosmology, lambda CDM, has been remarkably successful in explaining many aspects of the universe, but these new observations are poking holes in it, serious holes. So what are some of these alternatives? One prominent contender is modified Newtonian dynamics, or MOND. MOND proposes that our understanding of gravity itself is incomplete. Instead of invoking dark matter to explain the observed rotation curves of galaxies, MOND suggests that gravity behaves differently at very low accelerations, such as those experienced by stars on the outskirts of galaxies. For decades, MOND was largely dismissed because it couldn't explain certain cosmological observations as well as lambda CDM. But the Webb telescope's findings are forcing scientists to revisit MOND with fresh eyes. If galaxies in the early universe were indeed more massive and mature than predicted by lambda CDM, it might suggest that our understanding of gravity needs tweaking, just as MOND proposes. It's not just MOND either. Another alternative, known as the tired light hypothesis, suggests that photons lose energy as they travel vast distances through space, causing their wavelengths to stretch and mimicking the effects of an expanding universe. This idea was largely discarded when the cosmic microwave background radiation was discovered, as it offered a strong evidence for the Big Bang cosmology. However, some researchers are exploring modified versions of tired light that might be compatible with the CMB and other observations. Then there are models that propose variations in the speed of light. The speed of light, denoted as c, is one of the fundamental constants in physics. But what if it wasn't always constant? Some theories suggest that the speed of light was much higher in the early universe, which could solve certain cosmological puzzles, such as the horizon problem, the fact that the universe appears remarkably uniform in temperature despite regions being too far apart to have ever been in causal contact. These are just a few examples, and each model has its own strengths and weaknesses. But the common thread is that they all challenge the fundamental assumptions of the standard cosmological model. And the fact that these alternative models are being discussed more seriously now is a direct consequence of the Webb telescope's observations. Now, it's crucial to emphasize that nobody is claiming that the Big Bang is wrong, or that our entire understanding of the universe is collapsing. However, the Webb data is suggesting that our understanding of the early universe is far from complete, and that we may need to consider alternative explanations for some of the phenomena we observe. The implications of this are enormous. If we have to revise our cosmological models, it could affect our understanding of everything from the formation of galaxies to the nature of dark matter and dark energy. It could even lead to new discoveries in fundamental physics. One of the biggest challenges in cosmology is the problem of dark matter. We know that there's a lot of missing mass in the universe based on the way galaxies rotate and how light bends around massive objects. But we don't know what this dark matter is made of. It could be some exotic new particle that interacts very weakly with ordinary matter, or it could be something else entirely. The Webb telescope's observations could provide new clues about the nature of dark matter. If the early universe was different than we thought, it could affect the way dark matter interacts with ordinary matter. It could also affect the way dark matter is distributed throughout the universe. Or consider the mystery of dark energy. Dark energy is a mysterious force that's causing the universe to expand at an accelerating rate. We don't know what dark energy is, but it makes up about 70% of the total energy density of the universe. The Webb telescope's observations could shed new light on the nature of dark energy. If the expansion rate of the early universe was different than we thought, it could affect our understanding of dark energy. It could also affect our understanding of the ultimate fate of the universe. Here's what's wild. The Webb telescope isn't just confirming or denying existing theories. It's actively generating new questions and forcing us to rethink our assumptions. It's a reminder that science is a process of constant refinement, and that we should always be open to new ideas, even if they challenge our most cherished beliefs. It's also important to remember the scientific method. Scientists aren't just throwing out the old model because of a few new observations. They're carefully analyzing the data, developing new hypotheses, and testing those hypotheses against further observations. This is a rigorous process that takes time and effort. The analysis continued. What about the possibility that some of the discrepancies we're seeing are due to systematic errors in our observations or data analysis techniques? Scientists are constantly working to improve their instruments and methods, and it's possible that some of the problems we're seeing will eventually be resolved as our technology gets better. This means that the next few years will be an incredibly exciting time for cosmology. We can expect to see a flurry of new papers and conferences as scientists grapple with the Webb telescope's findings and try to make sense of what they mean. It's a time of uncertainty, but it's also a time of great opportunity. We're on the verge of a new era of discovery, and we're poised to learn more about the universe than ever before. And then there's the ongoing debate about the Hubble constant. The ongoing debate about the Hubble constant isn't just academic, it's existential. If the universe is expanding faster than we thought, our entire understanding of its history, composition, and ultimate fate is potentially flawed. This brings us to the future. What's next for the Webb telescope and this cosmic conundrum? First, let's examine the immediate plans. Astronomers worldwide are scrambling to use their allocated Webb telescope time to gather more data. We're talking about a coordinated effort to observe more distant galaxies, more Type 1a supernova, and more of everything that can help us refine our measurements of the Hubble constant. These observations aren't just about confirming or refuting the initial findings. They're about building a more complete and robust dataset. A dataset that can withstand scrutiny and provide a clearer picture of the universe's expansion history. Consider the sheer volume of data that Webb is capable of collecting. It dwarfs anything we've seen before. This means that scientists need to develop new and improved data analysis techniques to handle the influx of information. It's not just about taking pretty pictures, it's about extracting meaningful insights from complex datasets. Machine learning and artificial intelligence are playing an increasingly important role in this process, helping scientists to identify patterns and trends that might otherwise go unnoticed. The implications extend far beyond just the Hubble constant. If our understanding of the universe's expansion is wrong, it could also affect our understanding of other fundamental cosmological parameters, such as the age of the universe, the density of dark matter, and the equation of state of dark energy. All of these parameters are interconnected, and a change in one can have ripple effects throughout the entire cosmological model. This means that the Webb telescope's findings could lead to a major overhaul of our understanding of the cosmos. We might need to revise our theories of gravity, dark matter, and dark energy. We might even need to come up with entirely new physics to explain the observed phenomena. It's a daunting prospect, but it's also an incredibly exciting one. It's a chance to push the boundaries of human knowledge and to uncover the deepest secrets of the universe. The next phase involves a multi-pronged approach. Scientists will be using the Webb telescope to observe a wider range of objects at different distances, in an effort to map the universe's expansion history with unprecedented precision. This will involve studying the light from distant quasars, which can be used to probe the distribution of matter along the line of sight. It will also involve studying the cosmic microwave background, the afterglow of the Big Bang, which contains valuable information about the early universe. Scientists are also working on developing new theoretical models that can explain the Webb telescope's findings. These models will need to be consistent with all of the available data, including the observations from Webb, Hubble, and other telescopes. They will also need to be able to make testable predictions that can be verified by future observations. Here's what's wild. The Webb telescope is also being used to study exoplanets, planets orbiting other stars. By analyzing the light that passes through the atmospheres of these planets, scientists can learn about their composition and potentially even detect signs of life. This is a completely separate area of research, but it's also incredibly exciting and could have profound implications for our understanding of the universe. Meanwhile, there's the ongoing refinement of the cosmic distance ladder. This is the sequence of techniques astronomers use to measure distances to objects in the universe. Each rung of the ladder relies on the previous one, so any errors in the early rungs can propagate up and affect the entire scale. Scientists are constantly working to improve the accuracy of each rung of the ladder by using new and improved techniques and by cross-checking their results with independent measurements. This also involves a greater understanding of systematic errors. Are we truly accounting for every variable that could influence the measurements? Dust, gravitational lensing, the movement of the Earth, everything must be taken into account. This meticulous, sometimes tedious work is absolutely crucial. Scientists discovered that some of the discrepancy might be due to the way we're calibrating our instruments. The Webb telescope is incredibly sensitive, but it's not perfect. It's possible that some of the light from distant galaxies is being distorted or absorbed by intervening matter, which could affect our measurements of their distances. Scientists are working to develop new techniques to correct for these effects, but it's a challenging task. The implications extend to future missions as well. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will play a crucial role in this effort. Roman will have a wide field of view, allowing it to survey large areas of the sky quickly and efficiently. It will also be equipped with a powerful spectrograph, which can be used to measure the distances to millions of galaxies with high precision. And then there's the potential for entirely new discoveries. The Webb telescope is opening up a new window on the universe, and we have no idea what we're going to find. It's possible that we'll discover entirely new types of objects or phenomena that we never even imagined. It's a time of great uncertainty, but it's also a time of great opportunity. Further examination revealed that the early universe might have been more complex than we thought. There might have been more dark matter or dark energy present, or the laws of physics might have been slightly different. These are all possibilities that scientists are exploring. It's a reminder that our understanding of the universe is constantly evolving and that we should always be open to new ideas. The analysis continued, and with it the realization that the next decade will be pivotal. We're entering a golden age of cosmology with a wealth of new data and new theoretical tools at our disposal. It's a chance to solve some of the biggest mysteries in science and to finally understand the true nature of the universe. The data reveals that our journey into the unknown is only just beginning. But what if, despite all our efforts, the discrepancy remains? What if the Hubble constant refuses to conform to our theoretical models? That's a question that looms large, and it's something we'll need to address in the final section. 3.6 billion light-years. That's the distance to some of the galaxies Webb is observing that are just off. They're too bright, too massive, too old. We shouldn't be seeing galaxies this mature this early in the universe. It's as if they sprouted fully formed, defying everything we thought we knew about galactic evolution. If the Hubble constant discrepancy persists, despite our best efforts to account for it, we're left with a pretty unsettling possibility. It means that our standard model of cosmology, the framework that has guided our understanding of the universe for decades, is incomplete, maybe even fundamentally flawed. This isn't just about tweaking a few parameters or adding a new term to an equation. This could mean that we're missing a major piece of the puzzle, something so significant that it's warping our perception of the entire cosmos. Consider dark energy, for example. We know it's there, driving the accelerated expansion of the universe, but we have no idea what it actually is. What if our current understanding of dark energy is completely wrong? What if it behaves differently than we expect, especially in the early universe? Could this be the missing ingredient that's throwing off our calculations? And what about dark matter? We can detect its gravitational effects, but we can't see it directly. What if dark matter interacts with other matter in ways we don't yet understand? What if it's not just a passive background player, but an active participant in the evolution of the universe? It's something we're still so far away from fully grasping. It's not just the exotic stuff either. Perhaps our understanding of gravity itself needs revision. Einstein's theory of general relativity has been incredibly successful in explaining the behavior of the universe on large scales, but it might not be the final word. There are alternative theories of gravity that propose modifications to Einstein's equations, and some of these theories could potentially explain the Hubble constant discrepancy. The problem is, these alternative theories often introduce new problems of their own. They might explain one observation, but they could conflict with others. It's a delicate balancing act, trying to find a theory that can account for all the available data. Here's what's wild. The universe is a complex and interconnected system, and changing one aspect of our model can have ripple effects throughout the entire framework. It's like trying to fix a leaky faucet in a house built on sand. You might stop the leak, but you could also cause the whole house to collapse. Scientists discovered that one of the biggest challenges in cosmology is dealing with uncertainties. We can never know the values of cosmological parameters with perfect precision. There will always be some degree of uncertainty, and that uncertainty can propagate through our calculations and affect our conclusions. That's why it's so important to have multiple independent lines of evidence. We can't rely on just one type of measurement or one type of observation. We need to combine data from different sources using different techniques to get a more complete picture of the universe. The implications extend to our understanding of the very early universe. The period shortly after the Big Bang is still shrouded in mystery. We have some ideas about what happened, but we lack direct observational evidence. The Hubble constant discrepancy could be a clue that's telling us something about the conditions in the early universe. Maybe the universe expanded at a different rate than we thought. Maybe the laws of physics were slightly different. These are all possibilities that scientists are actively exploring. Further examination revealed that we might have to accept that our current understanding of the universe is simply incomplete. We've made tremendous progress over the past century, but there's still so much we don't know. The Hubble constant discrepancy is a reminder of that. It's a humbling experience to realize that we're still so far from understanding the true nature of the cosmos. But it's also an exciting one. It means that there are still big discoveries to be made, that there are still fundamental questions to be answered. The data reveals that this discrepancy isn't necessarily a crisis, but an opportunity. An opportunity to push the boundaries of our knowledge, to challenge our assumptions, and to develop new and more accurate models of the universe. The analysis continued, and it may require us to rethink some of our most basic assumptions about the universe. This could lead to a new era of discovery where we finally unlock the secrets of dark energy, dark matter, and the very nature of space and time. Consider this. The Webb telescope is providing us with a wealth of new data, and scientists are working tirelessly to analyze it. They're developing new techniques to correct for systematic errors, and they're exploring alternative theoretical models. It's a slow and painstaking process, but it's essential if we want to get to the bottom of this mystery. Scientists discovered that the next few years will be critical. As we gather more data and refine our analysis, we'll be able to narrow down the possible explanations for the Hubble constant discrepancy. We might even be able to rule out some of the more exotic theories. This means that the journey into the unknown is far from over. It's a reminder that science is a process of constant refinement, of testing and retesting our ideas against the evidence. And sometimes the evidence tells us that we're wrong. And then there's the potential for something truly revolutionary. What if the Hubble constant discrepancy is a sign of something completely new, something we've never even imagined? What if it's a gateway to a deeper understanding of the universe? The universe is vast and complex, and it's full of surprises. We should always be open to the possibility that we're missing something, that there's a whole new layer of reality waiting to be discovered. Here's what's wild. Even if we never fully resolve the Hubble constant discrepancy, the effort to understand it will have been worth it. It will have forced us to think more deeply about the universe, to develop new tools and techniques, and to push the boundaries of our knowledge. Measurements showed that, ultimately, that's what science is all about. It's about the pursuit of knowledge, the quest to understand the world around us. And even when we don't find the answers we're looking for, we still learn something along the way. So, stay curious, keep asking questions, and never stop exploring. And if you want to support this channel, hit that subscribe button.